Dear students, welcome to Digital Logic Design course. This is going to be our first lecture in this course. This lecture is more of an orientation lecture and you will be introduced to various aspects of the course. We will cover some introductory material from chapter 1 of the course textbook. The relevant sections for that material are 1.1 and 1.2. The objectives for our today's class include an introduction to the course, the grading policy that will be used throughout the course. We would also go through the contents of the course, including the lab experiments. And finally, we will cover some initial two sections from the chapter 1. This is the first course in digital systems and computing domain. Basically, this course deals with the basic concepts and the various tools that you will learn. These concepts and tools, they will be used to design, analyze various logic circuits. This course is a prerequisite for computer architecture course that you would be studying in the next semesters, as well as embedded systems, which you would be studying in the fifth semester. So mainly this course covers three or four main portions. One is the basic building blocks. Then we would go through the combinational logic. Then we will go through the sequential logic. And finally, we would conclude the course by introduction to memory as well as various programmable logic devices. So moreover, you would also be introduced to Verilog HDL. You almost half the labs that you would be performing, they include labs which are based on Verilog. So the different combinational, sequential, as well as the memory and other devices that we study, you are going to program them in Verilog and simulate them in model sim simulation software. The prerequisite for this course includes some basic knowledge of algebra that you might have acquired in your previous math courses. It's a 2 credit hour course, which means we will be having 2 theoretical classes per week and there will be 1 lab class in each week. The textbook that we will be following is Logic and Computer Design Fundamentals by Morris Mano. We will be using the 5th edition. The relevant details are available here. You can download it from the internet. For the reference books, we would be using Digital Design Principles and Practices by Wakerly. We will be consulting its 4th or 5th edition. You can get any one that is available, right? And for the Verilog hardware description language, we would be following the textbook that is the Verilog hardware description language, a guide to digital design and synthesis by Samuel Parnitkar. We will be using 2nd edition of this book. Okay, so these are the textbook as well as the reference book. The first one on the left, that is the Logic and Computer Design Fundamentals by Morris Mano. That's the main textbook, whereas the other two, they are the reference books. The lecture-wise breakdown is shown on this slide. Here you can see the lecture numbers along with the topic that is going to be covered in that lecture, along with the relevant section from the main course textbook, right? So as I've told you people earlier, there are 4 main portions of this course. The first course is about the basics. So the first 9 lectures, they are related to learning the basics. We would go through the number systems, the arithmetic operations that we can perform in different number systems, the various types of codes, the Boolean logic and gates. We would go through the Boolean algebra, manipulations using the Boolean algebra, in which we simplify some expressions using the Boolean algebraic rules and theorems. We would study the K-maps, right? And then we would conclude this portion by studying exclusive OR and exclusive NOR gates, and gate propagation delay. Then we would study some basics of the Verilog hardware description language. Once we are done with that, so then we would start the second portion of our course, that is the combinational logic design. We would study various portions that include the various combinational function blocks that include decoders, encoders, multiplexers, demultiplexers, the binary adders, subtractors. Once we are done with that, so then we would carry out some combinational circuit design as well. Then we would start with the sequential circuit design. We would study the latches and flip-flops, which are the basic elements for any sequential circuit. Once we have understood latches and flip-flops, then when we can carry out sequential circuit analysis and design, we would study state machine approach and some issues related to sequential circuits. Once we are done with the sequential circuits, we would learn some applications of the sequential circuits that include the registers as well as the counters. So this would be the third portion of our course. Once we are done with this, then finally we would study about memories. So we would study about random access memory, the static RAMs, dynamic RAMs, and we would study how we can combine different RAM ICs together in order to form larger RAMs, both in capacity as well as in width. And we would also cover some portions from the programmable logic device that includes the programmable array logic, programmable logic array, as well as the FPGA and programmable read-only memory. So this would be the entire these are the entire contents of this course. That was all for the orientation part of this lecture. Now we would start with the contents of the lecture. So the topics for today's lecture, we would go through what is a digital logic design, what are digital systems, and what are binary signals. A digital circuit is an electronic circuit that is built by connecting different components together. These components are called logic gates. A logic gate is an electronic device that is used to implement a logical operation. The basic logical operation include AND, OR, and NOT. These three gates, the AND, OR, and NOT, they are also called primitive gates. There are other variants of these gates which include NAND, NOR, exclusive OR, and exclusive NOR. Digital logic design is the process in which the functional design of a digital circuit is represented in terms of logical operation. Throughout the course, we would carry out digital logic design of various types of digital circuits, and we would try to implement various problems in terms of digital logic circuits. Since this course is about digital logic design, we need to understand the key differences between analog systems and digital systems. In our everyday life, both analog and digital systems are used to transmit and process information. Analog systems process signals which are continuous in nature. Such signals are represented by a time varying quantity such as voltage, and these signals can take an infinite amount of values. Examples include audio recordings and playbacks. Some older video formats such as VGA and S video are also examples of analog signals. On the other hand, digital systems process digital signals which have a discrete set of values. Digital signals, due to their inherent nature, they are discontinuous in nature and they can be represented using a finite set of values. Examples include an on-off switch that can be used to switch on and off a light. Similarly, the speech that I'm talking right now, the audio recording from the microphone, although it is analog in nature, but once it is recorded, it is converted into digital form and stored in the computer. Once you play the slides, this audio recording is played back and converted again from the digital format into an analog format. In real life, you would see a number of digital systems which have actually supplemented their analog counterparts. As we were talking in the previous slides that the digital systems, they have actually supplemented their analog counterparts. Over here you can see some examples. The first row contains some systems which are actually analog in nature, whereas the second row or the row at the bottom, it contains some digital systems which actually perform the same job as their analog counterparts. So the real world objects can gather data, they can display the data inputs either by using analog or digital means. The clocks, the multimeters and the joysticks, they can take either the analog form or the digital form. The only difference is the way the data is represented in both. In digital systems, information can be represented using discrete set of values. These signals in most present day electronic digital systems use just two discrete values, and therefore they are said to be binary. The two discrete values that are used, they are called 0 and 1. 0 is used for low, whereas 1 is used for high. These binary values of digital information in a signal is stored using physical quantities such as voltage. The high level or the 1 can be represented using 5 volts, and a low level or the 0 can be represented using 0 volts. There are two types of logic levels commonly used in digital logic: active high and active low. And sometimes you will encounter logic devices that uses both of them. Some signals might be active high, whereas there might be other signals which are active low. Active high means the signal will be performing its function when its logic level is 1. Here 5 volts represents a digital 1 and 0 volts represents a digital 0. On the other hand, active low means the signal will be performing its function when its logic level is 0. Here 5 volts represents a digital 0 and 0 volts represents a digital 1. There is an IC pinout which is shown at the bottom of the slide, that is the ICS74LS173. If you take a look at the pinouts, right, so you would see different signals which are not which are actually active high. Such signals include Q0, Q1, Q2, Q3, clock, ground, right? So it means there are some other signals like D0, D1, D2, D3, clear, VCC. So such signals would be indicated by a positive or the active high logic. So if you provide 5 volts to them, they will perform their functionality. If you provide 0 volts to them, they won't perform their functionality, right? So the 1 is indicated by presence of 5 volt signal, a 0 is indicated by the absence of 5 volt signals. This is what an active high actually means. On the other hand, you can see these two signals which are the E1 prime and the E2 prime, right? And we have OE1 prime and OE2 prime, right? There is a bar on the top of it, right? This indicates that these are active low logic signals, which means that if E1 is equal to 0, then E1 bar would be actually a 1. So these are active low logic levels. They would perform their functionality once their values are 0. In digital systems, the binary values of 1 and 0 are usually represented by range of voltage. In the figure on the right, a high output signal is actually represented by uh, uh, the voltage range of 0.9 to 1.1 volts, whereas a low output signal, it is actually represented by a voltage of negative 0.1 to zero point 0.1. Similarly, for the input, The high signal is represented by a voltage range of 0.6 to 1.1 volts, and a negative is represented by negative zero point 0.1 to zero point 0.4 volts. So this essentially means that if at the input our signal value lie between zero point 0.6 to 1.1, then we would take this signal as a high or a 1. If it lies between zero point 0.4 to negative zero point 0.1, we would consider the signal as a low, right? So why there is a difference between the ranges for the input and output, right? The If you see, this is the range for high at the input, whereas for the range for high at the output is this. So the ranges at the for the input, they are kept wider than as compared to the output in order to cater for variations due to noise and allow the circuit to function correctly. Somebody might ask a question that why are we restricting ourselves to binary signaling, right? We are only defining a high and a low. We can also define multiple signals, like there can be a 0, there can be a 1, there can be a 2, and there can be a 3, right? So these are called multi-level signaling, right? So if we are going for a multi-level signaling, then this entire voltage range, right, it needs to be divided into multiple ranges instead of just limiting to only high and low. So such signals, once we use multi-signaling, so the systems, then they need to be more efficient, right? And they become more complex since they need to distinguish between smaller voltage ranges. Since we are having multiple ranges, so the individual windows for each signal is going to shrink, and in order to recognize the level correctly, the system needs to be complex, right? And this complexity would actually translate into the cost of the system, right? And moreover, due to smaller voltage ranges for the multiple windows of the multiple levels of the signal levels, uh, what this would essentially mean that the system is also more vulnerable to noise, right? The system would be able won't be able to perform as much efficiently as a binary system, right? The system would be making more errors in because the windows are now smaller. A massive drawback of the analog systems is the possibility of interference due to noise. The variations in waves that encode the analog information are so small that it can be disrupted very easily by a minute interfering signal. In electronics, we call such an interfering signal as noise. There are two signals which are shown on the slide. The one on the left is actually an analog signal, whereas the one on the right, it is a digital signal. This is our source signal, that is theta s, right? This is an analog signal, whereas this is a noise, the second, which is actually added to this. So once these two source signal as well as the noise is added, this becomes our resultant signal, right? So if you take a look at the resultant signal, you cannot make out the original information by taking this resultant signal, right? So this is the actual problem that lies once we are dealing with analog signals and analog systems. On the other hand, if we consider the digital signals, this is a digital signals, like this is a 1, right? This is a 0, this is again a 1, 0, 1, and a 0, right? So this is the information which is encoded onto this wave, right? This is the noise which interferes with this, and this is our resultant signal, right? So once our digital signal and the noise, they are added, so we get this resultant signal, right? So if you take a look at this, you can still make out this is a 1, this is a 0, this is a 1, this is a 0, this is a 1, this is a 0, right? And remember those we were not using a fixed levels, right? We were defining ranges, right? So this means this is going to be categorized as a 1, this is going to be categorized as a 0, right? So this is the major advantage of working in digital systems or in the digital domain as compared to analog. Next, we would talk about the design process. So let's say we are given a problem and we are asked to design a system for that, right? So we will follow some procedure that we will call as the design process, right? So design is basically the process of understanding the relevant constraints of a problem, right? And then we arrive at the solution that balances those constraints. In computer systems, the typical constraints include functionality, right? That would be the major requirement. Then speed, cost, power, there might be power, some area restrictions, as well as reliability. So these all constraints, they needs to be considered, right? And considering these constraints, we need to develop a solution that addresses the problem. So this process would be called as design. In computers today, the leading edge integrated circuits, they have billions of transistors, right? So designing such an integrated circuit, one transistor at a time, it does not seem to be a feasible approach, right? So if we start with placing transistor by transistor, right, and we plan to fabricate the chip, right, so it would be a very difficult process to design and fabricate the chip, right? So in order to address this complexity issues, right, what we do is that we follow a top-down approach for designing the computer systems. So the specifications, they are actually highlighted at a very high level, and from those specifications, then we decompose the design into smaller blocks, right? And we keep on decomposing the those blocks into further sub blocks, right? This process is repeated until we reach a small block that is feasible for us to implement, right? So these modules or these blocks, they are then integrated in order to implement the required system as per the specification. So this process is also called hierarchical design, and we would study this in the detail in chapter number 3. Next, we would talk about the concept of layers of abstraction in computers. So one of the most important concept of computer system design process is the concept of layers of abstraction. So the goal of layers of abstraction is to reduce the complexity in computer systems. A computer system can be viewed at several layers of abstractions, right? With the circuits at the bottom, that is the bottommost layer, and algorithms, that is the high level, right? Or that is the algorithm layer is at the top, right? There are a number of layers in between these two layers, and each layer hides the complexity of the layer below. The goal is to remove the unnecessary implementation details about a component in the system so that the designer can focus on those aspects of the component that are required for solution of the problem. So the goal of this layered approach is to hide the unnecessary complexity and details which are not required for by the designer for solution of the problem, right? And using those abstractions, this designer actually arrives at a solution without going into unnecessary details. Right, so if we take a look at the figure, right, we already talked that at the top of the abstraction layers is the algorithms, right? So algorithms describes a series of steps that can be followed in order to solve a problem, right? You can think of it as a pseudo code which can be used to solve a problem. These algorithms, they are then implemented in different programming languages such as C, C++, Java, Python, etc. So the pseudocode, it is translated into a language which the computer understands. Then we have the operating system layer. So the operating system provides necessary software and hardware resources for execution of the program on the hardware. So both the operating system and the program, they are comprised of a set of instructions which are specific to the processor running them, right? And this set of instruction which is specific to the processor, this is called the instruction set architecture, or we call it ISA. The processor hardware is a specific implementation of the ISA, that is the instruction set architecture, and it is called the microarchitecture. A microarchitecture is a sequence of transfers between the registers of a processor. These register transfers can be decomposed into logic operations on set of bits performed by the logic gates. These logic gates are electronic circuits which are actually implemented using transistor circuits, right? So if you are going to write a program for computing the GPA of a student, right? So you do not need to worry about the logic gates and the transistor circuits, right? You are just going to write the code in the programming language, right? The rest of the details, the hardware resources, everything, that is automatically going to be looked after by these abstraction layers of architecture of this computing architecture. A number system is a mathematical notation used for representation of numbers. These are the symbols which are defined by us and they carry different values. There are a number of different number systems such as Arabic, Chinese, Roman, and many others. Positional systems use place value notation for representation of numbers. In such systems, a number is represented by a string of digit, and each digit has an associated value depending on its position in the string. Let's say we talk about the decimal number 1, 2, 3, right? So these different symbols, the 1, the 2 and 3, they have got different values based on their positions. The 3 is in the units place and it carries some certain value. The 2, it is in the tens place and it has a different value. Similarly, the 1 is in the hundreds place and it carries another value. If the position of one of these symbol is changed, then the value of the number would change. Each number system is indicated by a number called base or radix, and it is denoted by R. A positional number system of base R will have R basic symbols starting from 0 and it will go till R minus 1. For example, if we consider the decimal number system, so the base is 10, R is equal to 10, right? R is equal to 10, right? And there are 10 symbols starting from 0, right? Then we have 1 and it goes till 9. A number in base R with n digit integer part and m digit fractional part can be represented in this power series form. This might look a bit complicated, but we will consider an example. Consider a decimal number, that is 592.4. Since it is a decimal number, so R is equal to 10, right? There are 3 digits in the integer part, so n is equal to 3 and m is the number of digits in the fractional part. So there is 1 digit in the fractional part, so m is equal to 1. The same form can be written in the terms of numbers as 5 into 10 raised power 10 is the R, right? This is the same R. Then this 2 is n minus 1. N is the number of digits in the integer part. Over here it is 3. So 3 minus 1 is 2 plus the second symbol, which is 9, multiplied by base, that is 10, and this would be then n minus 2, right? And similarly this would keep on repeating, right? And this finally this would become plus 4 into 10 raised power minus 1, right? That is minus m, and m is 1. When the numbers are expressed in positional notation, we use the shorthand notation and only write the coefficient and the decimal point, right? The rest of the details are ignored since they are clear. So a number can be expressed as a sum of its integer and fractional part. This is the same power series that we saw in the previous slide. The four number systems that are commonly used include decimal, binary, octal, and hexadecimal. Decimal number system, the base is 10 and it includes 10 digits starting from 1 till 9. The binary number system, it is used in computers. The base is 2 and it contains 2 digits, that is 0 and 1. Each one of them is called a bit, which stands for binary digit. An octal number system, the base is 8 and we have got 8 symbols starting from 0 going till 7. And in hexadecimal, the base is 16. We have got 16 numbers starting from 0 going till 15. The numbers which are greater than 9, that is the 10, 11, 12, 13, 14 and 15, they are represented using alphabets A, B, C, D, E and F respectively. It should be noted here that in any number system there cannot be any number which is equal to or greater than the base. So if you take a look at the decimal number system, you won't see any number which is equal to or greater than 10. All the numbers would be less than 10. Similarly, in binary, you can see we have got 0 and 1, they are less than 2, and octal we have got 0, 1, 2, 3, 4, 5, 6 and 7, they are less than 8. And similarly in hexadecimal we have got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E and F, and all of them have values which are less than the base, that is 16. Okay, so in this lecture we have covered the first two sections of the chapter 1 of the textbook. Uh, you are expected to go and read section 1-1 and 1-2, right? The contents have been covered in the lecture, but you should give these two sections a reading. And there is an example 1-1, you should also read it, right? And try to understand the necessary details. Okay, so if you have any question, please mail me at my email address. Okay, so in the second lecture, we would cover different number systems. These include the binary, octal, and hexadecimal number systems. We would study how to convert numbers from one number system into another, and then we would study some arithmetic operations like addition, subtraction that needs to be performed in these different number systems.